All right, we're going to get started. Welcome, everybody. My name is Travis Kerrigan. I'm a senior engineer here at Pointwise, and I'll be your host for the webinar. With me is Carolyn Weber, the manager of our support and consulting group, and she'll be answering your questions at the conclusion of this webinar. So before I get started, I want to mention that all the Pointwise files that I use today will be made available online, as well as a recording of this webinar and a presentation outlining everything we're going to cover so you can download it for your reference. Okay? So the title of today's webinar is Meshing Forensics, How to Recover When Things Go Wrong. Occasionally when we're meshing, we encounter situations that we didn't quite expect, and we're not quite sure how to proceed past those situations that arise. And so that's what I'm going to cover today. We're actually going to encounter 7 of those situations through a series of application-based examples going through the entire meshing process. So we're going to talk a little bit about geometry manipulation and cleanup, surface meshing, all the way to volume meshing. Okay? So what you can see on the screen is very representative of a wing geometry brought into our software for meshing. It's fairly simple in that it's a single B-spline surface, okay? But it's also geometrically complex. It's highly 3D in nature. There's some sweep, some twist, and even there's a winglet. So this is something I sketched up in Pointwise to show. And a couple of things about this geometry. So in Pointwise, for those of you who aren't familiar with our software, we call geometry database entities. Okay, so in the drop-down database entities list in the list panel, you'll see that we have a model. A model is a watertight representation of the geometry. Okay, so it's really a watertight collection of quilts. So when we mesh on a watertight model, we're guaranteed that our surface mesh will also be watertight. So it's an entity specifically for the purposes of meshing. Okay, and I mentioned that a model is made up of quilts. In this case, we have a single quilt in this model. Quilts are nice because they represent meshing regions. You can lay up your quilts in much the same way you would lay up your surface mesh topology, because when you mesh a model, each quilt within that model gets its own domain. Okay, and a domain is our terminology for a surface mesh. So for example, if I grab this model and I put a surface mesh on it by clicking Domains on Database Entities in the toolbar, I'm just creating an unstructured surface mesh. I will shade it so it's a little bit easier to see what's going on here. If I zoom in here, you'll notice the leading edge is pretty crinkly. It's very faceted. We're not recovering any of the geometry at the leading edge using a single domain, a single quilt. Okay, so really what I need is, instead of messing with some of the unstructured solver parameters to refine based on curvature or deviation from the surface, I would like to use something that we call 2D T-Rex. It's a way for us to extrude these very regular stacks of high aspect ratio right-angled triangles. They're perfect for resolving high curvature areas such as this on the surface mesh level. But in order for me to do that, I need a connector, or what we call a connector is really a grid curve, running along the leading edge of this wing. Okay, now I mentioned that when you mesh a model, each quilt in that model gets its own domain. So in order to get a connector that runs across the leading edge, this model needs to consist of 2 quilts. One quilt representing the upper surface and one quilt representing the lower surface. Okay, so let me just undo that and show the geometry. So really kind of what I need to do here is split this model, okay, into an upper and lower surface. So what I'll do is I'll grab the model and I'll go to Edit, Split, and notice that the Split tool is not active. Okay, there's several reasons why a tool isn't active in our software. One is you didn't select anything. Another is that that tool does not support the type of entity that you've selected. In this case, this Split tool does not support this model that I've selected. Okay, but the trimming options are active. Okay, so what is splitting in our software? What exactly is splitting? Well, in fact, that tool takes on multiple roles, and I'll go into a little bit more detail about that a little bit later on. But a true split operation in Pointwise is a separation and reparameterization of the resulting surfaces. So for example, we have a single surface, we would split it into two physical surfaces, each with their own UV parameterization. Okay, that's a physical split operation. Okay, you cannot do that on the model level. Okay, it turns out that a model and a quilt, they're not real geometry. Okay, they're topology, and you cannot split topology because topology in our software does not have a UV parameterization. It's the underlying surfaces that have the parameterization, and you can go forward with the actual split operation. So what is topology? Well, topology really is just bookkeeping. It's just information about, who's related to a particular entity. So this model has some underlying quilts. Each quilt has some underlying trim surfaces, and those trim surfaces are subsets of some underlying geometry, like a B-spline surface. Okay, so we cannot split a piece of topology, but we can trim it. So that's what I'll do. With that model selected, what I can do is I'm just going to draw a database curve right along the leading edge of this wing. So I'm kind of approximating it. I have to select those points by hand. This is why some people prefer to go all the way down to the base geometry, because they actually know the UV location of the leading edge where they would like to split, and we'll do that in just a few steps here. So first we'll just split this, or we'll just trim this model by drawing a curve along the leading edge. So I've done that. I can grab that model and go Edit, Trim by Curve, select that curve and imprint. And you'll notice I end up with a model that consists of two quilts, one representing the upper surface and one representing the lower surface. And now when I select that model and I put a surface mesh on it, if I turn off the display of the database, you'll notice now I have a connector running right along the leading edge that I can use as a wall-type boundary condition for our 2D T-Rex unstructured solver. Okay, now I mentioned the split operation takes on multiple roles. Now what's this other role? Well, if I take these two quilts that I've just created by that trimming operation, if I assemble these into a single quilt, so you could imagine you're combining quilts into larger collections of quilts to help define your surface mesh topology prior to meshing. If you ever want to recover that, you can use the split tool. So if you notice this quilt that I joined those two quilts into one, this split option is now active. And at this point, it's more of a decompose command. Okay, so I have the ability to go back and decompose that quilt into its components because those underlying trim surfaces are still there. So I have the ability to back up. This is really beneficial, again, when you're joining large collections of quilts and you want to back up a few steps and decompose it. So if I click this button, I can now decompose that back into an upper and lower surface. Okay. So what if I want to go to the base geometry and operate on that and do a physical split operation at the leading edge location, a very specific UV location on that surface? Well, the way you do that is you would go to View, Show Hidden, because by default we hide those base entities. And so everything on top of this B-spline surface is considered topology. The trimming curves, the trim surfaces, the quilts, the models. Okay? So if we want to operate on the base geometry, we actually have to remove all the topology on top of it. Pointwise actually won't let me operate on that base geometry until I delete all of the topology sitting on top of it in this database hierarchy. The reason is because we don't allow those changes to propagate through that hierarchy. So if you're at the model level and you do those trimming operations, I mean, this is to prevent you from destroying your geometry. If you're at the model level and you're doing these trimming operations, okay, eventually you're going to do enough trimming operations if we allowed this to propagate to the base geometry that the original geometry would get flushed out of the undo stack and you would never be able to recover it. So this is trying to save you from destroying the geometry. And so if you want to operate on the geometry, you have to do so explicitly. So you need to show that geometry, delete all the topology on top of it by hitting the delete key. So now all I'm left with is the underlying B-spline surface, and I can actually split it at a given UV location, in this case a U of 0.5, V of 0, right along the leading edge, resulting in two B-spline surfaces, one for the upper surface and one for the lower surface. And now I can go and recreate all the topology on top of this geometry by clicking the Assemble Models button up in the toolbar. So now I'm left with a model consisting of two quilts. So that was going down to the base geometry and doing an actual split operation. Okay, so with that, we'll move on to the next part. So we're going to move more towards the surface meshing. Okay, so in this example, I'm going to finish assembling the solid model before actually doing the surface meshing. So I'm going to grab the model, go Create, Assemble Models, click Assemble in the toolbar, and you'll notice what I end up with are some red boundaries. Okay, what are those red boundaries? Well, those red boundaries are what we call lamina boundaries. So they represent things like holes or missing surfaces or gaps in the geometry that you can heal by increasing this edge tolerance. Okay, so here it's obvious that we're actually missing a surface at the inlet, so that's why we have some lamina boundaries there. But all these lamina boundaries on the interior represent things like gaps. Okay, on the inside here there's actually a valve, but before I change the edge tolerance, I'd really like to see what's going on the valve so I can ensure that I don't have any missing surfaces that I'm going to heal over. Instead, I would rather prefer to create those surfaces and then increase the edge tolerance to heal over any gaps in the geometry. So a lot of people ask, how can we visualize these lamina boundaries for very complex parts and assemblies outside of the model assembly panel? Okay, so what you do is you just accept the model as it is with its lamina boundaries, just grab all the quilts in the model, and go to the Attributes button on the toolbar, and change the color mode of the quilts to by topology and update the display. So what we end up with is the display has been updated. Now the quilts have been colored by topology, and we've recovered those lamina edges. And now what I can do is, if you have everything organized into layers and groups, you can isolate those. So for example, I have the valve isolated to a layer, and I can just go in and inspect and see that there are in fact no missing surfaces, and it's probably a good idea for me to increase that edge tolerance and heal over those gaps at this time. Okay, so this is pretty beneficial if you have very complex parts or assemblies where you can't quite see everything and you've already got things layered up. Okay, so this is what we call solid modeling. So we're actually healing the problems on the geometry level. But if you prefer, you can actually select that model and put a mesh on it, and go to Grid Merge and heal the problems on the mesh level. Okay, this is what we call fault-tolerant meshing. So here we can see the actual connector topology, and the red connectors are free connectors. So those are pretty much like our lamina boundaries that we saw when we were in the model assembly panel. Okay, so in this case we would be healing over the problematic geometry using the mesh. Okay. Again, if you want to be able to see the connector topology outside of this panel, the way to do that is just like before, except this case you're grabbing all the connectors, going to the Attributes panel, and changing the color mode to by topology and updating the display. Okay, and now you can see the connector topology in this way outside of the Grid Merge panel. All right, so I'm going to undo that and grab this model and just clean it up. So I'll go Assemble, Models, and in this case I'm just going to increase the edge tolerance to heal those lamina boundaries. So all I'm left with are the holes for the inlet and the outlet, but all the gaps have been healed by increasing that edge tolerance. So now we're ready to begin the actual surface meshing procedure. Okay. So here's the result after finishing cleaning up that geometry and quilting it up. One thing to note is this is actually a single quilt. I'm pointing that out because it's actually going to cause us some problems. Okay, so just keep that in mind. So if I grab this model and I put a surface mesh on it, just change the display of the domains to hidden line. Okay, so what I want to do is cap off the inlet here. Okay, so to do that I will grab the grid curves, what we call connectors, and use these as boundaries for the unstructured domain that I'm going to create. So I'll click Assemble Domains up here in the toolbar and create an unstructured domain. And this is the result of that operation. Not very pretty. If I do a drop down on the domains list, I can see that this domain actually consists of 40 points and 38 cells. Okay, but looking closely, it looks like none of those points are on the interior. In fact, they all seem to have snapped to the boundary of that domain. Okay, and in fact they have, and Pointwise does this on purpose because most of the time it actually works. This is one situation where it's not quite giving you the result that you want. What's going on is Pointwise says, okay, all of my boundary points are constrained to one quilt. That must mean all of the interior points for this domain should be constrained to that same quilt. And so that's what it's done. All the interior points for that domain have actually been snapped to the boundary. So it's pretty easy to fix. We can just change the shape of this domain from database constrained to free. So with that selected, we can go Grid, Solve, go to the Attributes panel. So in this Attributes panel, this is where we can change all the unstructured solver attributes specific to that domain, including its shape. So in the surface shape section, we would change the shape from database to free. And go Solve, Initialize. So we've freed those interior points. They're no longer constrained to the boundaries, and we get the domain that we wanted. Okay. All right, but something else interesting has happened. Okay, this domain is green, but all the other domains are purple. So why the difference in color? Well, it's a common misconception that the color refers to the database associativity of the domains, basically how constrained to the geometry they are. A lot of people believe that green domains are free, meaning they're not database constrained, where purple domains are database constrained. In fact, that's not true, and I can disprove that by grabbing some domains on the geometry and just starting to join them, and they'll start turning green. Okay. I can even go as far as grabbing that quilt and decomposing it into a left and a right half. And that domain turns green. I can actually grab that domain, and in the Examine menu down near the bottom, you'll see the Database Associativity tool. Okay, if I click on this, I can see how constrained that domain is to the geometry. And in this case, it's still 100% constrained. Okay, so the color doesn't have anything to do with how constrained the domain is to the geometry. What it refers to is the method of initialization. So a green domain goes through a 3D non-parametric meshing technique. It's initialized through a series of decimation, refinement, and projection steps, whereas a purple domain goes through a 2D parametric meshing algorithm. Okay. In this case, you see the purple domains are one domain per quilt, and that quilt has information about the underlying geometry and its UV parameterization. So it goes through this 2D parametric meshing algorithm. Whereas when we start joining domains over multiple quilts, those quilts know nothing about one another, and so it resorts to a 3D non-parametric meshing technique. Okay. Why is this important to you? Well, when you start joining domains on a model across multiple quilts, they'll start turning green. And I want you to know that doesn't mean that the domain is all of a sudden jumping off of the geometry. And you can quickly verify that by grabbing that domain and looking at its database associativity and ensuring that it is still on the geometry. Okay? All right, so now we're ready for some volume meshing. Okay, so we've cleaned up the geometry, we've got our surface mesh, we've assembled our block, which is our terminology for a volume mesh. It's just a definition of the volume without any interior elements. In order to populate that block with elements, we need to initialize it. So that's what I'm going to do. I'll grab that block and click Initialize up here in the toolbar. And I'll get a warning message. So Pointwise is telling me that one or more entities could not be initialized. Okay. Basically, this is saying that given the things that you gave the initialization, so the domains and the block definition, Pointwise couldn't construct a valid volume. Maybe there's domains intersecting one another, things like that. So it's not going to create the volume because it wouldn't be valid. Okay, so we'll click OK. So how can we prevent this sort of thing from happening in the future? Well, over the last few years, I've found a couple of techniques that are pretty quick to verify if your volume is valid prior to doing the initialization. Okay, they're very fast. One of those ways is by just doing a drop down on the domains list. Okay, and just organize it by cell count. And take a look at the very first entry in that list. In this case, I have a domain that actually has one cell in it. Okay, so this is a good way to identify these small sliver domains that may need to be either eliminated or joined with adjacent domains to create larger collections. So if you notice, all the other domains in this mesh have 500 or more elements. Okay, so this is a big red flag that, you know, all the other domains have 500 or more elements except for this one just has a single cell. Okay, how do we find it? Well, with it selected in the list panel, the way to do that would be to go View, Zoom, Zoom to Selection. The hotkey for that is Shift F2. And so I'll zoom and I'll just shade this domain so it's a little bit easier to see here. Okay, so there's that domain, and if I zoom out, it looks to be at the leading edge of the blade near the hub, and it actually looks like it's kind of piercing through the surface mesh of the blade itself. Okay, so this is definitely our problem. It could be here, maybe somebody else gave you this mesh, maybe you blindly selected all the geometry and just meshed it, and there was like a little surface there or something. It doesn't matter, we found it and we can eliminate that issue before we initialize the block. Okay, another way is by going to Grid Merge and looking at the connector topology. If you didn't explicitly create any baffles, basically interior domains that represent thin-walled structures or used for point control, if you didn't create any of those baffles, you shouldn't have any free connectors. And in this case, I know I didn't create any baffles in this mesh. And if I zoom in here, those 3 free connectors that are over here in the connector topology window are the 3 connectors that make up that single cell domain. Okay. All right. So let's say you actually go through with the initialization before doing those things. What you end up with in the message window are some error messages. It's basically telling you that, you know, for block 1, some points are too close or coincident. Some other points can't be inserted. But what it will give you is some coordinates, some XYZ values of those points. So in the notes that I'm going to provide, I copy this value, this XYZ value, and I create a database point. And then when you create that database point, you can do a drop down on the database list and organize by type to find that database point. This will really only work if you don't have too many database points already in your geometry. It also ends up, when you do that, you actually create an entity, which you may want to go delete later. Another way is to begin to create a connector. Okay, so that's what I'll do. I've copied that value. I'll click 2-point curves and enter that value as my first point and hit enter. And if I zoom out, now Pointwise is looking for me to pick the second point for this connector. Okay, but instead of doing that, because I don't want to create an entity and then have to go delete it, if you notice, from the first point I'm getting an arrowhead. Okay, there's an arrowhead coming out of that first point. So I can use that as kind of a guide to guide me to that location. And it just happens to be a point on that domain. Okay, so then I know that this has definitely got to be the problem area in my volume. So I can actually remove that. It's an interior face. I can actually remove that from the volume definition by grabbing the block and going Edit, Add Remove Faces. So I can actually add and remove faces at will to the block definition, and then say Begin Removing Faces, grab that guy, End Removing Faces, and OK, and I've basically eliminated it from the definition of the unstructured block. Okay. There's a couple other things I have to do to get this volume prepared. So I already have a volume prepared. In this case, it's all cleaned up. The T-Rex parameters have been set. For those of you who aren't familiar with our software and what T-Rex is, it's our unstructured viscous volume mesh generation technique. So I've already set up all the parameters. I'll grab that block and go Grid, Solve. And I'm just going to change the display style of the extrusion front to shaded and initialize. And what we're looking for here during the initialization is we're looking for stopped points. Okay, so it may not be reasonable for very complex grids to sit here and watch every step of the extrusion and find where these stop points are. But occasionally you can come back and check and see how many stop points there are. You'll immediately start to see them on the display because they're highlighted in red. And they can actually indicate areas that need a little bit more investigation. Okay, they could be stopping because they're violating quality criteria, or maybe they're just stopping because they've reached an isotropic state. So I'm going to watch this extrusion. It doesn't take very long. And notice that in the next step, I'm actually going to start to get some stopped points. Okay, so I'm getting some stop points at the leading edge and trailing edge near the hub and the shroud. And if I zoom in here, okay, I'm getting some stopped points here at the trailing edge and the leading edge. I'm going to pause this. Now you actually have the ability to pause the extrusion, which is pretty nice if you're examining it while it's extruding. You notice that the trailing edge is actually stopping. These points are stopping a lot faster than those at the leading edge. Okay, so if I zoom in here, it's not immediately apparent what's going on, but at least I can make a mental note that I should come back here and look at this area and see if there are any problems. Okay, so I can resume that and let it finish the extrusion. So that's kind of the benefit of watching the extrusion while it's taking place, is you can make note of where these stop points are and go through using some of our examine tools and see if there really are any problems in the mesh. Okay, so we'll let it finish out. Okay, so with that block selected, I'm going to go to the Examine menu. Now we have several different metrics you can look at, and people always ask, what's a good metric to look at? It's really dependent on the solver. Different solvers are sensitive to different metrics. One that I almost always look at for unstructured blocks is the maximum included angle. It kind of allows me to visualize, the element shape, whether it's like a pancake element or how skewed it is. So this is one I almost always use when I'm looking at an unstructured volume mesh. So I'll click that. Something else that I do is I turn on the histogram. It gives me an idea of where a majority of the elements lie in terms of quality. And I almost always adjust the maximum value on that color bar, maybe 150 or 160. And by doing that, I can see at the top of this bar, I can see I've got 177 elements with a maximum included angle above 160 degrees. Okay, and how can I see those? Well, the easiest way is just turn off the view of the domains. So all you're left with is kind of a skeleton, the connectors. And you can see those because those cells are highlighted in red. Okay. Now this really isn't telling me anything I didn't already know. I mean, these cells are in areas of collisions. So we have a front coming off of the blade and the hub and the shroud, and they're colliding. Really, a lot of these could probably be eliminated by adjusting some of the T-Rex solver attributes, things like collision buffer, some of the skewness criteria. But what I'm really concerned with is what's going on here at the trailing edge. It doesn't look like there's really anything else going on. And if I zoom into the trailing edge, I don't really see anything out of the ordinary except in those collisions. Maybe the best thing to do would be to take a cut and just kind of march backward to that area. Let's zoom in here and see if we can see anything. All right, so it looks like those cells coming off of the blade are pretty large. They have a pretty high aspect ratio to those compared to those coming off of the hub. Okay, so maybe we have a volume ratio issue going on back here at the trailing edge that just didn't come out when I was looking at the max included angle. So what I can do is just change the examine type to volume ratio. So now we're looking at the ratio of adjacent cell volumes. Okay, and the maximum is 27. I mean, that's pretty large. Let's turn on the histogram and see. And it looks like the majority of the elements have a volume ratio less than 3 or 4. Okay, so 27. I mean, that's a pretty large jump in cell size from one cell to the next. Let me just change the max to 10. Okay, it looks like, yeah, I mean, we have a little bit finer resolution here on the color bar, and it seems like the majority of the elements are definitely, they have volume ratios less than 3. That sounds a little more reasonable than anything over 10. And it looks like we have 251 elements with a volume ratio above 10. And in this region near the trailing edge, this kind of verifies what I was thinking back here. We have these really large volume ratios, okay, which were causing those stopped points that we were seeing during the extrusion. And if I turn on the view of the domains, I'm just going to isolate the blade, the hub, and the shroud. I think I know what's going on back here. If I rotate around, it looks like we just have a mismatch in spacings at this connector junction. Okay, so we've got these really tall cells next to some really small elements causing those large volume ratios and then the stop points during the extrusion. So for unstructured meshes, we recommend that at these connector junctions you have about the same spacing. Okay, so that's what I'm doing. I just copied the spacing and now I'm pasting it to that vertical connector. So now we have cell sizes that are roughly equivalent in this region at this connector junction, eliminating those large volume ratios and those stopped points. Okay, so with that, I'm going to pass things over to Carolyn. I want to mention that you can type your questions in the questions dialog box, and Carolyn will answer them at this time. Thank you all very much.
Hello, this is Carolyn Weber, and I'm happy to answer any questions that you have at this time. If you need to ask any questions, you can use the questions panel in GoToMeeting to type your questions in. All right, we'll wait a few more minutes and see if anybody has any questions. Okay, we have a question. A common problem that this user has is they are not able to join connectors or domains. That's actually a really good question. There's a couple of situations in which you might not be able to join connectors and domains. Let's start with connectors. For connectors, the first situation in which I've seen people not able to join connectors is if the end nodes of the two connectors are actually physically separated by some gap. When that happens, you can use the grid merge command, which you can see here. And you can go to the merge pairs of entities option and look at node-node intersection. So node-node essentially will look for gaps between connector and nodes. So you would simply just type in a tolerance, let's say 0.1. In this grid we don't have any gaps, so nothing's going to come up, but when I hit enter, it would show the pairs of node gaps that are existing in the mesh, if there were any, and then you could merge those and then join the connectors. Now, there are two other main situations in which you might not be able to join connectors. The second one is if it would destroy topology. Now, when I say destroy topology, what I mean is if you look at this example that Travis just had up, you see that we have this junction of 3 connectors. In this junction, I have 2 connectors here on the bottom that meet at a node, and then a third that comes down vertically and also meets at that node. In this situation, I would not be able to join these bottom 2 connectors together because there is a third connector at that junction, and it would destroy the topology in this region by joining these 2 bottom connectors. Now, additionally, there's one last reason why you might not be able to join connectors, which is if you had duplicate connectors on one side of this interface or another. So, for instance, let's say this third connector is gone here, and we've got these 2 connectors on the bottom. If I had 2 connectors lying in the same space on this side, then I would not be able to join across this node because technically there would still be 3 connectors that touch this node. It's actually another instance of the original case we talked about here with this T-junction, except for this top connector would be laying flat on the side here. Now, we have a user asking, how did we copy and paste the connector spacings? That's actually pretty easy in Pointwise. You can copy a connector spacing first by selecting the spacing. Then if you go over to Edit, you can do Copy. Now, when you get ready to paste that spacing, select the spacing that you want to paste it on, and then go back to Edit and use Paste Spacing. Now, if you're going to do this using your hotkeys, you would use Control-C to copy and then Control-Shift-V to paste. We're being asked if we're going to have recordings of this webinar, and we will. Those will be posted on our website within the next day or two. So you can just go back to our webinar website at pointwise.com and see a recording of this. Now, we're being asked if we will have a webinar about some of the common problems found in structured meshing. We don't have a specific webinar right now in the wings for problems with structured meshing, but I am sure we will be putting topics such as that together in the future. So just keep an eye out for our schedule of upcoming webinars, and we'll try to include that type of topic in the future. We're being asked what considerations regarding mesh quality verification should one make when scripting mesh generation for optimization runs. Is creating a complex base mesh and then just changing geometrical parameters using glyph to create various mesh instances a good idea? Is the scripted optimization of domains and blocks viable? And it is. I would say the thing that you need to keep in mind when you're writing a glyph script to create a parameterized mesh that's going to change is just basically what type of mesh are you creating? Are you creating a structured mesh, an unstructured mesh, a hybrid mesh, a T-Rex? The quality considerations for those types of meshes varies based on what meshing type you're actually creating. So you are going to want to build in some quality checks into your script. Say, for instance, for an unstructured T-Rex mesh, I would always want to check my maximum included angle for the volume mesh and make sure, let's say, that it's below 170 or 175 for any run. So I would always incorporate some type of quality check at the end of my script. So as I run through creating my parameterized meshes, if one of the meshes exceeds that quality parameter, I'm aware of it and I can go back and see what the issue was. So it's quite viable, and we build it into most of our scripts. So we have a question: is Pointwise much better than GridGen? I love this question, and the answer is a resounding yes. Pointwise has GridGen's features. As you guys know, GridGen was around for, or has been around for over 25, 26 years. It might be more. And Pointwise has all the features that we've developed over that course of time in GridGen, and it also has additional features that we never had in GridGen. We have some more automated options in Pointwise that we didn't have in GridGen, and we've really made Pointwise a much easier product to use. The interaction with Pointwise takes much fewer mouse clicks than it did with GridGen, so you'll find that you get projects done a good deal faster. And if you're interested in finding out more about Pointwise, you're always welcome to attend one of our training classes. We have them here once a quarter in our offices at Fort Worth. They're free for current customers, and it's really the best way to get up to speed quickly on Pointwise. Now, what are some of the other ways that we can improve or examine the quality of pyramids and prism cells? All right, now when it comes to prisms, it really depends on how you're creating those prisms. If you're creating a prism by doing an extrusion of an unstructured mesh, the best way to make sure you're getting high quality prisms is to make sure you have a high quality surface mesh first before you do the extrusion. And you can see from what Travis did here with this case where he made sure that the spacings at this node junction were the same. This is probably one of the biggest things you can do to make sure you have a high quality unstructured surface mesh is to make sure you have consistent spacings at node junctions. Now when it comes to pyramids, pyramids are created in pointwise unstructured meshes when there is a structured domain present in an unstructured block. The best way to ensure you have a high quality pyramid in that case is beware of including very high aspect ratio quads in that structured domain, because those will create very high aspect ratio pyramids where the vertex of the pyramid is very close to the bottom face of the pyramid. That's going to have a high maximum included angle, and it's going to cause a lot of issues down the road in your flow solver. So just be careful of how high your aspect ratio is in your structured domains when you include them in those unstructured blocks. Now, we have a question about the T-Rex generation. We went through the T-Rex generation in this webinar without explaining how it was done. Do we have any tips on the best practices for T-Rex? We actually have a couple of other webinars that already deal with how to generate T-Rex meshes. They're available on the webinar page at pointwise.com, and I strongly encourage you to go through and watch those webinars. I think they're going to help you out a lot with learning how to use T-Rex. If you'd like further tips on how to use T-Rex and really leverage it for your project, you're always welcome to call us at support@pointwise.com, and one of us will personally work with you on your case to help you get the highest quality mesh you can. Now, when generating prism layers, if you run into collision issues, what is the first knob to turn? That's an excellent question. When you're generating a T-Rex mesh and you have a collision, the knob that you want to turn in that case is the collision buffer. Now, I don't have a block available right now, but the collision buffer is in here. Let me pull up something we can look at. Okay, wait just 1 second. All right. Okay, we still don't have a block available. So let me pull up something really quick where we can show you this option. Sorry, looking for something right now. Oh, still no block there. All right, so I'm going to go ahead and move on and just pull up one of our tutorial files, which I know already has a block that we can use. So I'm going to go to the C drive, and I'm going to go to Program Files, x86. This is typically where Pointwise is installed on each machine. There's the Pointwise folder, and in Pointwise v17.1r2, you'll see a tutorials directory. If you look in there, there's a Wingstore T-Rex folder, and it has actually the final version of the grid for that tutorial, and that's what we're going to look at. So this will allow us to select a block once I turn on our block selection mask, and then go to Grid, T-Rex, and Attributes. Well, actually, we just want to go to T-Rex. The advanced attributes for T-Rex down here right beneath the layers frame, select that and open it, and you're going to see an option here for collision buffer. This is probably the most powerful setting you can change if you know you're going to have a gapped region in your grid where the fronts are going to collide. By default, it's set to 0.5. Whenever I know I have a gapped region in my grid, I typically crank this up to a value of 2.0. And what that does is it looks at the height of the last cell that T-Rex creates, the last layer, and then it says, okay, based on this height, multiply that times the factor here in the collision buffer, and that's the space that I need between those two approaching fronts to insert isotropic cells. So this allows you to get a much better quality mesh in those gap regions. Now, on to our next question. On the first wing example, how would you resolve the leading edge curvature and put more cells in that area? I would actually create a T-Rex surface mesh on the leading edge of that wing. So I would first create an unstructured domain on the top and on the bottom. Then I would select that domain, and I would go to Grid T-Rex, and just on the leading edge connector, I would have it grow cells. And what that's going to do is it's going to give you a very structured looking cell in that area of high curvature, and it's going to really reduce any faceting you might have and give you a much clearer picture of what the surface of the wing looks like. Now, do we currently have any plans for examining the mesh while we are solving? Right now, we do have a feature request to give access to the examine command while you're in the solver. But that is currently not implemented. So we do have that on our list for a future project. Now, we have a question about how do you shift among adjacent entities as the X key does in GridGen. If you're in Pointwise and you want to bounce amongst different entities, let's say connectors. I'm going to turn on our connector selection mask here, and I'm going to zoom in on the wing of our plane. All right, and you notice I've got quite a few connectors down here, and as I hover my cursor over them, they highlight in pink. If I just hit the space bar, this space bar will cycle between the various entities that I have available. Also notice that if I hit my space bar, down in the lower right-hand corner of my screen, the probe also changes between those. So as I highlight a different entity, it tells me that currently I have connector 4 highlighted, and it has 21 grid points. Now as I hit the space bar again, I have connector 1 highlighted and has 66 grid points. So you would use the space bar instead of the X key. Let's see. Now, the next question is, okay, we have a user that says they know something that Gridgen does, but Pointwise doesn't. So when you get a chance, please definitely share that with us. We'd like to know. We have a user that would like to know how to measure the distance between the vertices in Pointwise. Okay, this is very straightforward. So I'm just going to zoom in here, right? And we're looking at the symmetry plane and the top of the wing. So what I want to do is I want to measure the distance between this vertex and this vertex on the surface. To do that, I'm just going to hold down the Alt key and then right-click the first point. You'll notice I get this little circular cursor. Okay, and also look down in the messages window and see that it showed me the XYZ location of that first point. Now, I'm going to hold down the Alt key and right-click my mouse on the second point. Now, first it gives me a dashed line that indicates the straight line distance between those 2 points. In the display window, it also shows me the physical distance between them, which is 0.0126. And when I release my mouse button down in the messages window, it shows me the XYZ of the second point and also reiterates what the distance was between it and the first point. All right, so those are all of our questions. Are there any other questions before we wrap this up? Okay, so those are all the questions. So what we're going to do is we're going to go ahead and close the webinar. We appreciate all of you joining us today and all of your wonderful questions. We will be placing this recording on our website within the next day or two, so please keep an eye out for that. And also, please review all the previous websites we've done. You might find some very useful information there, and keep an eye out for all the ones we've got coming in the future. So thank you, and have a great day.